Welcome to Calculus.
We overcomplicate even the simplest task.
On this episode, Stevenson will demonstrate
Let's look at another example of related rates. So this says water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is exactly 6 feet deep? So our first step here is to create some kind of picture to help us make sense of what we're dealing with. So they tell us the tank is conical. So what they're telling us is it's a cone. And they tell us that it's point down. So draw your cone. And what we know is it has water running into it. And because we have and then we have a base radius, right? And then we have a height of this. So we know the base radius, so if you can imagine, let's kind of go all the way down like that. So we have a base radius of 5 feet. And we have a height of 10 feet. Okay. And what we know is the water is going in at 9 cubic feet per minute. It's asking us how fast is the water level rising when the water is exactly 6 feet deep. So what we need is now an equation that can connect what we're talking about here. We are talking about volume. They're telling us it's water filling into a tank, and this is volume. I know it's volume because it's a cubic unit. So volume of a cone is 1/3 pi r squared h. So from here, this formula just connects volume as a fixed value. Nothing's moving. But we know something's moving. The water is running in. So as the water's going in, this water level is rising. So what we're going to do now is take the derivative of this equation with respect to time on both sides. Now we have our related rate equation right here. Let's make our list of variables and operators off to the side so we can get a sense of what we have, what we need, and where we go from here. Now, let's kind of look at this and give some perspective. The tank stands point down and has a fixed height and base radius. How fast is the water level rising when the water is 6 feet deep? Okay, so they're talking about the height of the water level. So we need to introduce another variable. That we're going to make our height. So this is the height of the volume of the water level there. Okay. So we know that H is going to be 6. We know dV dt, so how's the volume changing? Well, it's changing at 9 cubic feet per minute. We don't know how fast the radius is changing. dH dt is how is the height changing. That's actually what it's asking for, right? How fast is the water level rising? So that's our unknown. But we also don't know this radius is going to refer to the radius in there. So we have a problem. We have two things we don't know. So like in our previous examples, we have to use some sort of other concept or connection to help us figure this out. In this particular case, we can use similar triangles. Now you haven't seen similar triangles since IM2, but if you look carefully right here, you can see the similar triangles. I'll redraw it right here for you. So what we need to do is use similar triangles to make a connection between the radius and the height. And from there, that'll help us with dr dt and what r is. So with similar triangles, remember, once you have them, you just set up a proportion. So I'm going to say, let's see, the inside triangle, so radius over height equals, now we look at the big triangle, 5/10. So if I simplify this, I basically get the radius is 1/2 times h. So what I did is I simplified 5/2 is 1/2, or excuse me, 5/10 is 1/2, and then I multiplied by h on both sides. So the radius is half the height. Okay, so that's super helpful. It's asking me when the water level is 6 feet. So that means when the height is 6. So if the radius is half of that, based on these dimensions, that means if the height is 6, then what's the radius going to be? Well, it's half of 6, which is 3. Cool, so we found one of them. Now we got to figure out this dr/dt. Well, we can use this equation here that relates radius and height, and we can do exactly what we did up here. We can take its derivative, and then we'll have a dr/dt and a dh/dt. So let's do that next. So if I take the derivative of r, I get dr/dt, and when I do the derivative of 1/2 h, it's just 1/2 dh/dt. So how does this help me? Well, now I know that dr/dt is just half of whatever dh/dt is. So where it says dr/dt, I'm going to write 1/2 dh/dt. Now I have everything that I need right here for my equation up here in orange. So I'm going to take my numbers, 9, 1/2 dh/dt, 3, and 6. I'm going to plug it into here. The only thing I won't know is dh/dt, but that's what I'm trying to find. I'm trying to figure out how is the water level rising. And so since it's rising, I would expect a positive value here. So I'm going to plug in my numbers, and then I'm going to simplify.